Good morning, friends. We are learning our subject, that is data mining 3160714. And in that, we are learning our chapter 3, that is concept description and association rule mining. Right? Let us see the summary of previous lecture. What we were learning? We were learning the dynamic item set counting DIC algorithm. Now in that we were talking of that we are having the lattice wherein we are having the items, then combining them we can have the item set like 2 item set, 3 item set, 4 item set, right? That we can have. In that we are using say circle and rectangle, or we can say box. Fine. There we are using solid box, solid rectangle, then solid circle, then we can say dash circle, dash box, right? All the things we have talked of a bit. Let us recall them. When we see solid, it means confirmed. What confirmed? That depends on whether it is circle or box. Dashed, that means suspected. Box, that means frequent. Circle, that means infrequent, right? Then solid box, that means confirmed frequent, right? Solid means confirmed, box means frequent. So confirmed frequent. Fine. Then solid circle, that means confirmed infrequent. Dashed box, that means suspected frequent, and dashed in circle, that means suspected infrequent, right? So we read AM transactions at a time, right? Whatever AM is there, that is being specified in the problem. In first pass, one item set counts are changed typically, and we consider few 2 item set, isn't it? So typically we say that in the first pass, 1 item set counts are changed, or you can say they are getting confirmed. In second pass, 2 item set counts are changed typical, right? We may consider 3 item set, right? It depends on the way it is being traversed, right? Or you can say the way the transactions are there, fine. Just recall, okay? Then we can see the particular example and we can have the idea, fine. Okay, now transitions of dash to solid, right? Dash to solid, and from circle to box. See, dash means what do we say? What do we say? Dash means suspected, right? From suspected to confirmed, right? Suspected to confirmed. Okay. And infrequent to frequent, right? What we want to say here is dash means suspected, solid, that means to frequent, and what do we say? Confirmed. Dash means what do we say? Suspected, and solid means confirmed. Circle to box, that means infrequent to frequent. Fine. So what can be there in the transitions? That is dash circle. Dash, dash means suspected, right? Circle means infrequent. Suspected, frequent. Suspected, frequent to suspected, frequent, right? Suspected, infrequent to suspected, frequent. Then what do we say? Dashed box to solid box. suspected frequent to confirmed frequent, right? If count is greater than or equal to minimum support, we'll be drawing the lattice, and in that we'll be putting the dash, circle, then box, solid box, right? All those things we'll be doing. So graphically we'll be calculating the example for this particular algorithm, that is DIC, right? Okay, so dash box to solid circle. If count is less than minimum support, dashed suspected, box frequent, right? Suspected frequent is converted to solid circle. That means confirmed infrequent, right? When the count is less than minimum support. Fine. So this is what is there in our mind, and now we are calculating the example. Fine. Let us proceed. The example is given where transactions are given, the TID, that is T1, T2, T3, T4, and the items, whatever are there in that transaction, that is given. Now here, the items are being represented as 1 and 0. It is not the count. I mean, we can say A is having, say, 1, 2, 3, 4, 5. So 5 should be there. No, that count is not there in this transaction table. It only conveys that when this is 1, it means A item is there in transaction T1. So if I want to say about T1, what it is having is A comma B, right? Because for A 1 is there, and for B also it is having 1, right? So for T2 what do we say? It is only A, and for T3 what do we say is it is having B and C, fine? Okay, so this is what is the interpretation of this example, this transaction table. Okay, now minimum support given is 25%, and M, that is number of transactions we read, is given as 2. You can say actually 4 transactions are there. So 2 only. Why? The way we are reading the transactions and updating our lattice, that is M is equal to 2 given, right? So at a time we can say we'll consider first transaction and second transaction, and we update our lattice. Fine. So that way we can say that we are reading, say, M transactions, and we update the lattice. Okay. Now what is the minimum support? That is 25%. So what is the minimum support count? That is 25 divided by 100 multiplied by 4. That is total number of transactions, and that is equal to 1. Fine. Understood? Proceed. Now, what we are learning? Dynamic item set counting, that is DIC algorithm. Fine. Okay. Now, item set lattice for the transaction database. Which items we are having? We are having only A, B, and C, right? So how do we represent that lattice? That is already known to us. First of all, let us consider the empty item set. Then after we are having A, B, and C. Then after we'll combine them to have the next level, or you can say one item set is there. So we are generating the 2 item set, right? Okay. So A, B, C. So we can be having AB, AC, and BC, right? And if we go one level above, we can be having the A, B, and C, right? How to make this lattice is already known to you. We have already seen that. Fine. Right. Now, proceed. Item set lattice before any transactions are read. Nothing is read just now. Okay, nothing is read. So, first of all, we should have the counters. for each and every item, that is A is equal to 0, B is equal to 0, C is equal to 0. Right? Okay. Now, empty item set is marked with a solid box. Empty. Empty. Right? Nothing is there in it. So, it is confirmed frequent. Right? So, it is marked as solid box. All one item sets are marked with dash circles. One item set, it means single item. A, B, C, dash circle. Dash means suspected and circle means infrequent, right? So that is what we have marked here. Fine. Now, after M transactions are read, M transactions, M was given 2, right? Okay. So, what was there in T1 and T2? T1 is AB and T2 is A, right? So, what will be there for the counters of A, B, C? And will we have any other count? Let us check it out. A. In T1 transaction A is there, in T2 transaction also A is there. So the count of A will be equal to 2. For B, only once the B is there, so B is equal to 1. And C is equal to 0, right? C is equal to 0 because it is not found. And yes, A, B, because A and B are red, we can have the idea about that also. So that also what we are doing is we are having AB, right? AB is equal to 0. Now we have to mark all these things in the lattice figure, right? Now how to do that? We are saying that after M transactions read, M means 2 transactions we have read. So T1 and T2 we have read, right? Now, what we have to do? Before this, these 3 A, B, C were dashed circle, right? Okay. So now what we do is we change A and B to dashed boxes because their counters are greater than minimum support. So what to do? We are making the dashed box, right? Or dashed rectangle, fine, for A and B because their count is greater than or equal to minimum support. What is minimum support we have calculated? That is equal to 1, right? For support count, minimum support count we have calculated that was 1, right? So A is crossing, B is also crossing. If not crossing, it is equal, right? So the condition is fulfilled, right? Okay. So for them, we are putting them as dashed box, and for C is equal to 0, so we are keeping it as it is. And AB is equal to 0. So we'll start that with dashed circle, right? Dashed circle. Why? Because both of its subsets are boxes. Boxes means suspected frequent, right? So if the subsets are suspected frequent, then its superset we can have it as the dashed circle, right? The rules we have already seen. Fine. Now, after 2M transactions are read, what do we mean by 2M transaction? One transaction, that means M, right? Sorry, not one. M transaction means 2 transactions we have read. Okay, now 2M transactions. So 2 into 2, that means 4 transactions are read, right? So first M we have considered. Now let us consider the 2M, that is the remaining 2, right? So T3 and T4. T3 and T4. T3 is C and T4 is empty. So what will be the counter? A was 2, B was 2, was it? B was 1. B was 1. So what do we say? B is coming to 2. Where is the transaction? T3 is B, right? BC. T3 is BC. Yeah, here B is remaining. T3 is BC, right? B comma C, we used to say, isn't it? So what do we say is the count of B was 1 and now we are reading B. So count of B is coming to 2. For C, it was 0. So now it will come to 1, right? Now it will come to 1. For AB, AB was counted. Yes, it was counted. Where it was counted? Here in T1, right? A and B was there. So AB was counted means not its counter is incremented, but we can say that at least it is encountered during the pass of transactions, right? So what we are doing is we are adding the counter for those two item sets, right? And that is equal to 0. We are initializing that. See, for any counter, first of all, it is getting initialized to 0. Then after we change it, right? Okay, so AB is equal to 0. Now we have encountered AC. AC is here? No, but here we are having. So we have considered it as 0. BC. BC we have encountered? Yes. Here it is there. So we'll consider BC is equal to 0. Fine? Okay. Now C changes to a square because its count is greater than minimum support. C is 1. Is it greater than minimum support? Obviously, because minimum support is 1 only. So, this is greater than minimum support. B is also greater than minimum support and A is also greater than minimum support, right? So, they are now becoming confirmed frequent, right? Okay, so we are marking them as solid box or solid rectangle. Fine. Okay. What we say is ABC have been counted all the way through. So we stop counting them and make their boxes solid. What do we mean by all the way through? Counted all the way through? That means what? See, it means that we have scanned all the transactions once, right? We have scanned all the transactions once. In M, that is in, you can say, first of all, we read first two transactions because M is equal to 2. Then after again we have read two transactions and now that is after having first pass of all the transactions. That means all the items are being counted for single item set or you can say one item set. Fine. So we are saying that A, B, C have been counted all the way through. So we stop counting them and make their boxes solid. If they are counted, that means should we have to make their boxes solid? No. We have to make their boxes solid only if their counter is greater than or equal to the minimum support, right? Greater than or equal to, here typically we are saying better to write is this way, right? Greater than or equal to, fine, minimum support. So we make A, B, C as the solid boxes. Add counters for AC and BC. Because what? Their subsets are all boxes. If their subsets are not boxes, we will not consider the dash for their super set, right? Okay. So here, as this BC and AC, that is A and C, B for they are the subsets of this A, B, AC and BC, right? So what do we say is, as they are boxes, we are marking this pair, two item set as dash circle. You can say this, it was already there, fine. But for AC and BC, now they are having their subsets which are all boxes. So we'll mark this AC as dash box, sorry, dash circle, and for BC also we are marking as dashed circle. Fine? Okay, let us proceed further. Now, after 3M transactions, that means again first two transactions are red, right? First two transactions are red. So what will be there? Let me put the transactions here so you can have the idea. What is there for T1, T2, right? You have the idea, right? But you may not remember what is there in the transaction. Better to put it here, right? So you can see that properly and you can remember that also properly, isn't it? Now, T1 and T2, right? So what we have? Counters. A is equal to 2, B is equal to 2, C is equal to 1. Should we again increment the count for single item set? No, we should not. Because they are counted all the way through all the transactions, right? Okay, so we'll now not increment the count for one item set, but now we will consider the two item set because this is second pass of transactions, right? Okay, so now what we will do is, as we are counting A, B, we'll increment the count of item that is A, B. And as it is counted 1, we will say it as AB is equal to 1. Should we consider AC is equal to 1 and BC is equal to 1? Obviously not, because that is not being considered here. Fine. Here, do we have AB here? Sorry, AC here? No. BC here? No, we do not have. So we'll not consider that. Fine. So AB has been counted all the way through its counter and it satisfies the minimum support condition. So we change it to a solid box. BC changes to a dashed box. BC changes to a dashed box. Can we have that here? Should we change it to dashed box? Do we have anything here? Do we have anything here that is it having one count or two count? No. Then we should not change it to dash box. We'll keep it as circle only. Fine? Only. It is not changing. It is same, right? It remains same here. Fine? Okay. So now what we want is for other transaction, what is there? For this 4M transaction, what is T3 and what is T4? T3 is, it is what? T3 is BC, right? It is BC. And T4 is nothing, that is empty. T4 is empty set, right? So now we again have to count. Fine. So I'm putting this for you only. Otherwise, when you are calculating in the notebook, you can see that and you can do it very easily, right? So now, what was that? For the counter, single item set, A is equal to 2, B is equal to 2, C is equal to 1. It was that. AB is equal to 1. That was there, right? AC is equal to 0, BC is equal to 0. That was there after 3M. Now, after 4M, T3 is red. So BC is there. So BC is equal to 1. AC, can we say anything about AC? It is 0 only, right? It is 0 only. Now what is that? This is the second pass where we have read all the transactions by two transactions first and then two transactions, right? That is 3M and 4M transactions. That is what we have read. So now we can say that the count for the two item set is typically confirmed, right? So we can say AC is equal to 0. Now AB is equal to 1 is greater than or equal to minimum support. BC is equal to 1, that is also greater than or equal to minimum support. So for BC and AB, we will mark them as solid box. What about AC? AC is equal to 0. It is less than minimum support. That means it is confirmed infrequent. So we'll mark it as solid circle. Fine. So what do we say? AC and BC are counted all the way through because all the transactions are read in second pass. So the count, or you can say boxes or circle, that way we will consider them as confirmed, right? And that is for two item set, right? We do not count ABC. We are not counting ABC. Why not? We should consider, no? Should we? Let's see that. Because one of its subsets is a circle. Here we can see AB is, we can say, confirmed. BC is confirmed. AC is confirmed, but it is infrequent. These two are frequent. AB and BC are frequent, but AC is infrequent, right? So when it's one subset is infrequent, this cannot be frequent, right? So what we do is we are not counting, or we are not considering anything for ABC. Now, is there any dashed item available in this lattice? No. That is what is the terminating condition of this algorithm. So, what do we say? The algorithm is done, right? So now, what do we say? This particular algorithm in comparison of a priori algorithm, right? So what do we say about a priori algorithm? It is much faster than the brute force algorithm. It avoids checking all items, all elements in the lattice. What we are doing is we are having the comparison, isn't it, of the algorithm which we have just studied. Fine. Pruning really prunes in practice. It makes multiple passes over the data set. That is for our, what we say is a priori algorithm. Here also we are having multiple passes, right? One pass for every level k. But here we are having one pass for every level K, right? Multiple passes over the data set is inefficient when we have thousands of candidates and millions of transactions, right? See, we are discussing the a priori algorithm only, but we can consider in the comparison of our DIC algorithm, do we have the same thing available there? There we are representing it using the lattice and dash and solid circles and boxes, right? Here what we are saying is a priori algorithm is faster than the brute force algorithm. That is where we are considering everything, but it avoids checking all items, all elements in the lattice, right? Okay, and what do we say is multiple passes over the data set is inefficient when we have thousands of candidates and millions of transactions. Fine. So what do we do? For limitations of a priori algorithm, removal, we do have the algorithm. Next we want to study is pattern growth approach, and that is mining frequent patterns. Okay, mining frequent patterns without candidate generation. Pattern growth approach, that is mining frequent patterns, and that is without candidate generation. Our priori algorithm, we used to say that the bottleneck, it is breadth first search, and you can see that too many candidate generations are there. That is candidate generation and test often generates a huge number of candidates. The FP growth approach is depth first search. It avoids explicit candidate generation. See, this algorithm which we want to study is fantastic. It is better than that of our a priori algorithm in the way that it is having depth first search, and it avoids explicit candidate generation. Wow. Major philosophy, it grows long patterns from short ones using local frequent items only. That means ABC is frequent pattern. Get all transactions having ABC, that is project DB database on ABC. D is a local frequent item in database where ABC is that. It implies ABCD is a frequent pattern. ABC was frequent, D is local frequent, so we can say combination of them will also be frequent, right? So this is what we are considering. Pattern growth approach, mining frequent patterns, and people say it as FP growth, right? Frequent patterns, right? So FP for pattern growth, it is growth, right? So FP growth approach, or people say it as FP tree also, fine, algorithm. So what to do for that? Mining frequent patterns without candidate generation. Compress a large database into a compact frequent pattern tree, that is FP tree structure. Highly condensed but complete for frequent pattern mining, right? It avoid costly database scans. Develop an efficient FP tree based frequent pattern mining method. So what is that? A divide and conquer methodology. Decompose mining tasks into smaller ones. It avoids candidate generation, sub-database tests only. So what is there in this particular algorithm? First, create the root of the tree labeled with null. Scan the database D a second time. First time we scanned it to create one item set and then L. That is frequent one item set. You can say, ma'am, where did you say this? It is there in the same statement. Fine. So first of all, create a root tree that is with the null. Then after what we say is we consider the one item set count, that is we'll find the support count of each and every single or individual item. Then we'll check for the minimum support condition and we'll be having the L, that is we can say L1, that is one item set frequent patterns, right? Okay, now the items in each transactions are processed in L order. That is, we'll be having sorted order. What do we mean by that? If bread is having count 5 and we can say that that butter is having count 3, will be having bread first then butter, right? The way we are having highest count will be sorting the items. Fine. Okay, now a branch is created for each transaction with items having their support count separated by column. That means we'll be writing it as say item I is there. So I colon its count, suppose 2, right? So this way we'll be writing. And here what do we consider is say bread colon 5 comma say butter colon you can say 2 or 3, right? So this way we should consider. Fine. We'll have the example. You can be clear with that. Let us have the idea what we actually have to do. Fine. Okay. Now, whenever the same node is encountered in another transaction, we just increment the support count of the common node or prefix. To facilitate tree traversal, an item header table is built so that each item points to its occurrences in the tree via a chain of node links. Now, the problem of mining frequent patterns in database is transformed to that of mining the FP tree. So instead of the whole database, now we are having the FP tree. From that, we'll get the frequent patterns, right? We do not have to scan the database again and again, right? Okay, so let us proceed. What are the advantages of the FP growth algorithm? The biggest advantage found in FP growth is the fact that the algorithm only needs to read the file twice as opposed to a priori algorithm who reads it once for every iteration, right? Another huge advantage is that it removes the need to calculate the pairs to be counted, which is very processing heavy because it uses FP3. This makes it order of n, which is much faster than a priori algorithm. The FP growth algorithm stores in memory a compact version of the database. Now, let's see the algorithm example, right? Okay, so the transaction and items, that is the TID and the transaction items, they are listed in this table. Okay, now, what is given? First thing is 9 transactions are there. What is minimum support? Minimum support is 2, that is support count is given as 2. So what is the minimum support in percentage? That is 22 percentage, right? And minimum confidence given is 70 percentage, right? It is given 70 percentage. Now we have to first find out the frequent item set using a priori algorithm, that is one item set, right? And then association rules will be generated using minimum support and minimum confidence. Fine. Okay. So now what we do? We have to scan the database and find the support count of it. Of it means items, right? And then after we need to check it with the minimum support and find the L, that is L1. One item set frequent items. Okay, so now what do we do? The support count is for I1 6, I2 7, I3 6, I4 2, and I5 2. Now compare with minimum support. So what will be having? I2 is having 7, I1 is having 6, I3 is having 6, and I4 is having 2, I5 is having 2. Are they crossing the minimum support? Yes, of course they are crossing. And now what we do is we sort this item count, support count, where the support is greater than or equal to minimum support. How do we sort it? We sort it in the descending order, or we can say that what we are doing is item which is having the highest support, we are keeping them first and then after the other ones, right? Okay, so what we are having for sorted L, this sorted L is very important because based on that only we will consider all the transactions. Fine. Okay, so sorted order is I2 7, I1 6, I3 6, I4 2, I5 2, right? So I2, I1, I3, I4, I5. That is what is the order. Fine. Okay. Proceed further. Now, what we are having is, yeah. Now we build the tree. That is, we go through each of the transactions and add all the items in the order they appear in our sorted list. Fine. So what do we say? For transaction, that is I1, I2, I5. So should we have to traverse in that way? No, we do not have to. We have to consider according to the sorted list. And according to that, it is I2, I1, I5. Now, that way we have to make the tree. First of all, we know that we have to make the null node. Then after first transaction, we are traversing. So first of all, I2 is there. Then after I1 is there. And then after I5 is there. So for all of them, we'll set the count is equal to 1. Right? For all of them, we are setting the count is equal to 1. Because once only we have traversed this particular nodes. Clear. Okay. Fine. Let us proceed. Now, we build a tree, right? We know that. So for second transaction, add I2, I4. Should we consider I2, I4? No, we should check first of all what is there in the sorted order. So for that, we are having the order that is I2, I4 only. So no issue. Now, where to go? From null. Do we have I2 available? Yes, it is there. So we'll increment the count of this I2. What was that? It was 1. It was 1. So we'll increment that to 2. I2 is there. Now after that we are having I4. Do we have I4 available here in the previous transaction? In the previous tree, we were not having. So we'll generate a new branch. So we can say we are having I4 and its count is 1. Do not confuse that here also we should give it as 2. No, because this node is considered first time. So its count is 1. Fine. Let us proceed. Now, the transaction next is I2, I3. What is there in the sorted order? That is I2, I3 only. So, let us start from null. I2 is there? Yes. So, increment its count. What was there in the previous transaction? It was 2. So, we'll increment that to 3. Now, I3 is there. Do we have I3 in the previous transaction? Is it there in the tree? No, I3 is not there. So we will add one new branch, and that is I3, and its count is set as 1. Fine. Its count is set as 1. Now, I1, I2, I4. The next transaction is I1, I2, I4. But according to the sorted list, we should have this transaction as I2, I1, I4. So start from null. I2 is there? Yes. If it is there, then increment the count. I1 is there? Yes. It is there in the root, in the path. So we can increment the count. After that, I4 is there. Do we have I4 available? Let's see the previous transaction tree. Do we have I4 available here? You can say it is here. But it is for I2, I4. And what transaction we are having is I2, I1, I4, right? The path is to be followed, right? The path is to be followed. So I2, then I1. So we incremented the count for them. And I4, which is not available in the path, we have to create a new node for that. Okay. Now for fifth transaction, I1, I3. According to sorted list also it is the same. You can say null. I1 is there here in the path, but that is I2, I1. Do we have null and directly I1 available? No, we do not have. So we have to add a new branch where we'll be writing I1 as 1 and I3 as 1, right? Now, next transaction is I2, I3. And according to sorted list also it is I2, I3. So null, then I2 is there? Yes. So increment the count. I3 is there? Yes. It is also there in the path. So increment the count for it. Next transaction is I1, I3. For that also we have to check. I1, no, in this path it is not there, but in this path it is there, right? I1, I3. So we'll increment the count for I1 and I3 both. Okay. Now, next is I1, I2, I3, I5. But according to the sorted list, we are having I2, I1, I3, I5. And what we have to do is increment the count if the node is revisited, right? For I2, we increment that. What was there? It was 5. Now it is incremented to 6, right? I2. Then I1, right? It is also incremented. Then I3, that path is not there. So let us create a new branch for that. That is I3 is 1 and I5, that is also equal to 1, right? That is also equal to 1. Fine. Next transaction is I2, I1, I3 according to sorted list, right? It is I1, I2, I3, but according to sorted list, it is I2, I1, I3. So let's see from this. Null. I2 incremented. Then I1 incremented. I3, yes, this path is also there. So let us increment that, right? In previous tree, it was having 1. So now in this tree, it is having 2. Fine. Now, in order to get the associations, now we go through every branch of the tree and only include in the association all of the nodes whose count passed the threshold. What is the threshold? That is minimum support. Fine. So, what do we say? I2, I1, I2, 7, I1, 4. That is available for all these branches But, but, but. This I5 is 1. Is it crossing or is it satisfying the minimum support condition? No, it does not. Because minimum support given is equal to 2. So cross this branch. Right? Red crosses there. Same for this one, that is I4 1. Cross this. Right? Cut it. For this I4, do we have the count which is greater than or equal to minimum support? No. So cut this. Right? Getting it? Fine? Okay. And what do we say about I2, I1? What should be the count for that? That is equal to 4. Why 4? Why 4? I2 is having 7 and I1 is having 4. So why I2, I1 is 4? Because whatever is minimum out of this, that is common to both. Right? So what do we say is equal to 4 divided by total 9 transactions, and that is equal to 44 percentage. Right? We can count for all other branches. Say I2 7, I1 4, I3 2. So whatever is the minimum that we will consider. So 2 divided by 9, that is equal to 22 percentage. Fine. For say I2 7, I3 2, what is minimum? That is 2. So 2 divided by 9, that is 22 percentage. Fine. Same way for I1 2, I2 2, what do we say is minimum is 2. So 2 divided by 9, that is 22 percentage. Fine. So associations are, say I2 I1 is 44 percentage, I2 I1 I3 is 22 percentage, I2, I3 is 22 percentage, and I1, I2 is 22 percentage. Right? That's all for today.